All right, this absolutely follows from statement 2. What you don't want to do so don't do these. What you don't want to do is something like right, as a step 3. We have no reason for stating that, right? That is, we could write the statement P of n plus 1 says this. That's a correct statement, right? But to simply write this, we've written down P of n plus 1, we haven't proven it. And it doesn't follow from any of these steps that we've already written. So this, at that point, your proof becomes invalid. Okay? Another thing you don't want to write is, so here's what we plan to write for step 3. A few people did something like this. Right? And that's a really slippery slope to a bad time, because this is not a proposition. P of n is an English statement, and taking an English statement which says that this is equal to that and trying to add something to it, there's no well-defined notion of that, right? This is like saying x equals 5 plus n plus 1, or if it's sunny I'm out on a run plus n plus 1. Right? And I understand the spirit, which is to take this left-hand side of P of n, this summation, and then add an extra n plus 1 to it, right? But make sure you're being really precise here, okay? Think of the person reading this as some automaton that only understands the strictest notion of propositional logic. So really, you know, if this is what you mean, spell it out. And that was the only real issue I saw in the proofs where I saw issues was the formulating of this notion. Once you get to here, then you do the algebra, which everybody seemed to know how to do. This left side can be written as sum from I equals 1 to n plus 1 of I. And this right side, you go ahead and you do your gymnastics. Now, without ever looking at P of n plus 1, you've proven that this summation from 1 to n plus 1 of I is equal to n plus 1 times n plus 1 plus 1 divided by 2. And that's a fairly happy result. And that's all algebra. And now you can say P of n plus 1. And the reason why P of n plus 1 is true is the definition of P of n plus 1 and the thing that we just showed in step 4. And so P of n implies P of n plus 1. And so P of n for all n bigger than or equal to 1, and that's mathematical induction. So your quiz Friday will be a couple of inductive proofs, similar to what you did on the homework. And I'm thinking 25 minutes for 2 proofs. So 10 minutes apiece and 5 minutes to do whatever. So does that make sense? Okay, so if you're still not clear what the difference is between different ways to do it, why would this be right, why would that be wrong, right? Definitely come and talk to me. I've got hours tomorrow morning starting at 7, so come by if you have questions. So on Monday, we had stated this: given n plus 1 positive integers less than or equal to 2n, one divides, at least one divides another. So n plus 1 integers from 1 to 2n, at least one of them is going to be divisible by another, and it's guaranteed. And so we can prove this with the pigeonhole principle. So let the n plus 1 integers be n1, n2, now let me call them a's, a1, a2, all the way up to a n plus 1. Okay, write a1 as 2 to the I1 times q1. A2 is 2 to the I2 times q2, and so on. an plus 1 is 2 to the in plus 1 times qn plus 1, where q1, q2, and so on are odd. So we want to factor out as many powers of 2 as we can from each of these a's, and then think of a as that power of 2 times an odd number. So if a1 is 18, this would be 2 times 9. If a2 is 20, that would be 4 times 5. If it was 100, it would be 4 times 25. If it's 64, it would be 64 times 1. All right, so the QI are odd. So we note each Q sub I is less than or equal to 2 to the n. Because each QI is less than or equal to AI, and each AI is less than or equal to 2n. Okay, for any n, the number of odd integers less than or equal to 2n is equal to what? How many odd integers are there from 1 to 2n for any n? I don't know, but you can play with some cases and make a reasonable guess.
Well, it's going to be half of 2n, maybe, plus another one.
Plus maybe another one, right? So let's say n equals 1. How many odd integers less than or equal to 2? Just 1. If n equals 2, we're looking for odd integers less than or equal to 4. That's 1 and 3. There's 2 of them. If n equals 3, we're looking for odd integers less than or equal to 6. That's 1, 3, and 5. There's 3 of them. And we could make an inductive proof if we were really being picky, and we could convince ourselves that the number of odd integers less than or equal to 2 times n is n. And that's a correct result. Well, the set of QI is a set of, let me not use this, so Q1, Q2, up through Qn plus 1. These are n plus 1 odd integers less than or equal to 2n. So this is where we throw in the pigeonhole principle. How many odd integers are there less than or equal to 2n? There's n of them. So make yourself n containers and put each of these qi into a container matching its value. Since we have n plus 1 objects going into n containers, at least one container has at least 2 things in it. So that means at least 2 of these are the same. So at least 2 of these q's are the same odd number. So now we do something that can be abused, but we're not going to abuse it. We're going to say, without loss of generality, let's just assume A1 is equal to the I1 times Q, and A2 is equal to 2 to the I2 times the same Q. So if Q3 and Q7 were the 2 Q's that were the same, I'm just renaming my starting A's. So I'm going to use A1 for A3, and I'm going to use A2 for A7. I'm just going to rewrite this whole thing from the start, and now it's going to turn out A1 is 2 to the I1 times some fixed number Q, and A2 is 2 to possibly different I2 times the same Q, right? And let's assume that I1 is less than I2. If I1 and I2 are equal, then right there we know that A1 and A2 are the same number, and so A1 divides A2, right? So presumably these n plus 1 positive integers you picked all had to be distinct. Otherwise, one of them automatically divides another. So if we assume I1 is less than I2, then we can write I2 equals I1 plus some delta, where delta is bigger than 0. It's my only chance to use Greek letters. And so I can write A1 equals 2 to the I1 times Q. A2 is equal to the I2 plus delta, sorry, the I1 plus delta times Q equals 2 to the I1 times 2 to the delta times Q equals 2 to the delta times 2 to the I1 times Q equals 2 to the delta times A1, and so A2 is a multiple of A1. And so that proves our result. And basically comes down to taking each of your n plus 1 numbers, write it as an odd number times a power of 2, and then observe with the pigeonhole principle that at least 2 of those odd numbers are the same. And so this is 2 to something times that odd number Q. This is 2 to something else times that odd number Q. And the larger of those will be a multiple of the smaller of those. So not an obvious result, but it's true nonetheless, and it comes from the pigeonhole principle. All right, and there's a generalized pigeonhole principle. So the pigeonhole principle talks about n containers and n plus 1 objects. The generalized one is given k containers and n objects, and you place objects into containers, at least one container has at least, and we have a funny symbol here, n over k objects, where this funny symbol, these brackets without the bottoms on them, where this is the ceiling operator, and the ceiling works like this. Ceiling of x equals the smallest integer bigger than or equal to x. So let's look at the ceiling operator first. Smallest integer bigger than or equal to 2 is 2. Smallest integer bigger than or equal to 2.1 is 3. Smallest integer bigger than or equal to 2.99 is still 3. Smallest integer bigger than or equal to 3 is 3. But if you take the ceiling of something slightly bigger than 3, it jumps up to 4. So if we apply the generalized pigeonhole principle to k containers and k plus 1 objects, this tells us that at least one container has at least ceiling of k plus 1 over k objects in it. Well, k plus 1 over k is just 1 plus 1 over k. And so this is some number slightly bigger than 1, but as long as k is bigger than 2, right, this is less than or equal to a half. So this is some number bigger than 1 but less than 2. This is equal to 2. So the generalized pigeonhole principle tells us if we have k containers and k plus 1 objects, at least one container has at least 2 objects, which is the particular pigeonhole principle we started with. So this generalizes it. So the ceiling operator is useful. So an example of this, you have 52 cards, and you have 4 different suits of cards: clubs, diamonds, hearts, spades. How many cards must you draw in order to guarantee you have at least 3 of the same suit? So 52 cards, 4 cards of each suit. How many cards do you have to draw to guarantee that you've got at least 3 of the same suit? Could be 3 diamonds, could be 3 hearts, could be 3 clubs. Doesn't matter, but you want to guarantee that you've got at least 3. And you know, it's possible you could just draw 3 cards and it's club, 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 and you're done, right? But you can't guarantee that if you draw only 3 cards, you're going to have 3 of the same suit, because you might draw a club, diamond, and heart. So how many do you have to draw to guarantee you've got at least 3 of the same suit? So we want to put this in the language of pigeonholes.
39?
That sounds high.
Yeah. I was thinking it's like, isn't it 12 or 13 cards?
13 each suit, right?
So, I'm assuming you would have to fill 3 suits, but...
No, you only need to have 3 of the same suit.
Yeah.
So one way to sort of without doing CSE 215, one way that you can approach these things sometimes is just try to imagine yourself being really unlucky. Okay? Like you have to pay $1 every time you draw a card. So you want to, get 3 of the same suit without paying out too much money, right? But imagine you're really unlucky. That's what it means by guaranteeing that you've drawn enough cards. So keep drawing cards, and no, I don't have 3 of the same suit. I don't have 3 of the same suit. I still don't have 3 of the same suit, right? How can you be terribly unlucky? So, you might draw a club, and then a diamond, and then a heart, and then a spade. And then your 5th card is going to be one of these, right? Maybe it's a club. But you're not going to draw another club, because that would be lucky, right? So we'll do another diamond and a heart and a spade. So I've drawn 8 cards, and I still don't have 3 of one suit. But you can kind of see whatever the next card is that you draw, you're either going to have 3 clubs, 3 diamonds, 3 hearts, or 3 spades, right? So from that kind of pessimistic analysis, it looks like you might have to draw 9 cards. But it's not a proof, right? But it gives you an idea of what the answer might be. So let's make some containers. Let's make 4 containers. 1 for each suit. And let's take n cards and put that into 4 containers. And the pigeonhole principle tells us that we're guaranteed at least one container has ceiling n over 4 objects in it. Well, if a container has 3 objects in it, it means those 3 objects have the same suit. If a container has 2 cards in it, it means those 2 cards have the same suit. So we can rephrase this question as find the smallest n such that ceiling n over 4 is equal to 3. Actually greater than or equal to 3. And then if you pick fewer than n, right, we know that ceiling n over 4 is going to be less than 3, which means it's possible that your objects will all have only 2 or fewer objects in them. Your containers will have 2 or fewer objects in them. So if you find the smallest n such that this is equal to 3, that's the first n for which you're guaranteed at least some container has at least 3 objects. In other words, you've got 3 of the same suit. So ceiling n over 4 equals 3. Well, we know that if n equals 12, 12 over 4 is 3, the ceiling of that. But if you go back and you look at how the ceiling works, right, as soon as you're slightly beyond the integer, your ceiling function jumps up to the next integer. So if we can make n over 4 slightly greater than 2, right, maybe make n over 4 equal to 2 plus some epsilon. Now I've done it. I've done an epsilon and a delta in the same lecture. If we can make n over 4 equal to 2 plus some small amount, that's our minimum value of n. So n is smaller than 8, right? This will be smaller than 2. n equals 8. 8 over 4 is just 2. 9 over 4 will be 2.25. That's going to ceiling up to a 3. So 9 is our smallest number. And a lot of these word problems with pigeonholes, right, are phrased in the terms of what's the smallest number, what's the fewest number, such and such to guarantee this or that, right? And they come down to basically trying to solve this equation. The concept is far more important at this point than the mechanics of working the problems. And a lot of these problems, like, prove one thing is a multiple of another, they're not obvious, at least to me. Right? They were thought up by very clever people. But the concept of pigeonhole principle, that's what we're after for the most part. All right, so on to permutations. Yeah.
I'm just trying to understand this, but I think I got it, but I think the key thing is to understand that you're only worried about getting 3 in any one of the 4 containers.
Right, right.
I got it.
Okay.
Yeah.
All right, so definition, a permutation is an ordered arrangement of objects. So this is different from sets. We're very much concerned with the order in which these objects are placed. So a permutation is an ordered arrangement of objects. And sometimes we'll talk about an R permutation, which is an ordered arrangement of R objects. So for example, suppose we're giving a set containing 3 objects A, B, and C. So ABC is a permutation of those objects. ACB is another permutation, as is BAC, BCA, CBA, CAB. Each of those is a permutation of those 3 objects. And I'm pretty sure those are the only permutations of the objects. So each of these is a permutation. Okay, an example of a 2 permutation might be A followed by B. It's an arrangement of 2 objects. B followed by A is another 2 permutation. What would be another one?
There's
$100
for a permutation.
combination of B and A into one symbol? I don't know.
No, think simpler than that. Give me an ordered arrangement of 2 objects from that set. Pick 2 objects from that set.
B and A?
B and A, give me an ordering of them.
A, B, or BA. Those are the
A, B, or BA, right? Okay, pick 2 different objects.
CD.
CB, okay. Give me an order. You want to do CB? That's a 2 permutation. Is there any other order I could put those in? I could do BC. That's another 2 permutation. Are there any other 2 objects I could pick from that set and arrange in a way that I haven't already listed?
You can pick AB, AC, and BC, 3 different combinations of 2.
So I could do AC. And what was the other one?
CA.
CA, good. Anything else?
I was just picking the combinations of letters, of 2 letters you could pick, just A, B, BC, and CA.
Yeah,
And then with those 3 combinations, you
permuting them.
found all of them.
Right, right. Okay, good.
You can't permute with the empty, can you, with an empty?
Empty set's not an element of this,
Okay.
right?
Oh.
So what about 1 permutations?
A, B, C.
A is a good one, B is a good one, C is a good one, and that's it. What about 0 permutations?
No.
Yeah, it's kind of like the empty string, right? No objects selected, and it doesn't matter what order we put those no objects in, so it's just kind of an empty set. So there's really none of those. There's 3 of these, there's 6 of those, there's 6 of those. And we can't talk about a 4 permutation if we only have 3 objects. because we can't pick 4 objects.
So
from
the
set.
null set is not.
Null set is not a permutation, but the 0 permutations might be, right, there are no 0 permutations.
So it's only a subset, right?
Yeah, yeah. All right, so what can we do with our permutations? So, given 11 students, pick 3 to give this invisible $100 to that I keep threatening to give. So given 11 students, you want to pick 3 of them to receive $100. Well, we want an ordered combination. So pick 3 to give a prize. $100, $50, and $20. Okay, how many ways can we do this? How many ways can we pick 3 students out of 11 to give this set of prizes to? We can think of this in terms of permutations as how many ways can we select 3 students from this group of 11 and place them in a particular order? In other words, how many ordered arrangements are there? So the number of ordered arrangements of 3 objects taken from the set of 11.
Well, we just saw in the last example you gave that there, if you pick any 3 objects, you can order them in 6 different ways.
Mm-hmm. True.
Then all we have to figure out is how many different groups of 3
Right.
students can we pick.
Right. So the number of 3 permutations of 11 objects. Well, we can go back to the product rule and answer this with what we did the other day. Our task is to pick 3 students to win these prizes, right? So, so how do we do this? Well, first we pick the prize, pick the student who's going to be first, right? So task T1, procedure 1, is pick the first student who's going to win the first prize. How many ways can we do that? Right, there's 11 ways to do that. And then we have to pick the student who's going to get the second prize, and it's kind of implicit in here, these are different students who get these, right? So for T2 we have 10 to choose from, and then for T3 we've got 9 students to choose from. And so the total number of ways we can pick 3 from 11 is 11 times 10 times 9. So whatever that turns out to be, 990 or something. And this kind of calculation comes up a lot. So we have a language for representing this. So we could say P11 comma 3. That's the number of 3 permutations from 11 objects. And more generally we can say Pn comma R equals the number of R permutations of n objects.
Could you do it like, you didn't use what I just said?
No, we're actually going to use what you said when we talk about combinations.
Okay.
That's going to get us from permutations to unordered arrangements. But yeah, you could do that. All right, so number of R permutations of n objects, we can use the same product rule analysis. So T is the task. Of picking R objects. And we can break that down into a series of subtasks. T1 pick the first object. T2, pick the second object. All the way down to TR, pick the rth object. Alright, if we have n objects to pick from, the number of ways we can pick the first object is n. The number of ways we can pick the second object is just n minus 1. The number of ways we can pick the rth object is n minus, and if you work the math, it turns out to be r minus 1. So P of n comma r is just n times n minus 1 times n minus r minus 1. And don't worry too much about the details of this minus 1 plus 1 business, because we'll do some examples and we'll see what this boils down to very quickly. But we're going to simplify this expression. This is actually n times n minus 1 times n minus r plus 1. And I'm going to multiply this by some more stuff. N minus r minus 1. Let me work on a bigger sheet of paper. So n minus r minus 1, n minus r minus 2, n minus r minus 3. You can do that all the way until this comes down to 1. And I'm going to divide it by the same thing. So I've done my favorite mathematical trick of the week. I've multiplied something by 1. So this original expression, which is the number of R permutations of n objects, is really just equal to this times 1, right? But I can rewrite this top part as this is the product of all the integers from 1 up through n. That's just n factorial. And the bottom part is the product of all integers from 1 up through n minus r. That's just n minus r factorial. And so this is a formula for the number of R permutations of n objects. And so factorials will figure prominently in everything we do for the rest of this unit. So the number of two permutations of three objects, n equals 3, r equals 2, this would be 3 factorial over 3 minus 2 factorial, which is 6 over 1, which is 6. There's our 6 objects. If r equals 1, the number of 1 permutations should be 3 factorial over 3 minus 1 factorial, which is 3 factorial over 2 factorial, which is 6 over 2, which is equal to 3. There's your 3 objects. The number of 3 permutations, if r is equal to 3, that's 3 factorial over 3 minus 3 factorial, which is 3 factorial over 0 factorial. So what's 0 factorial? Yeah, it's kind of weird. That's equal to 6 over 1, which is 6. If we try this for 0 permutations, r equals 0, This is 3 factorial over 3 minus 0 factorial, which is 6 over 6, which is 1. So there is 1 0 permutation, which is you don't select anything. So that still works. So it's a general formula. So the number of 5 card hands from a deck of 52 cards. And we're supposing that the order in which you pick these cards is significant. If you're playing poker, the order doesn't matter. But the number of ways that you could take 5 cards out of a deck of 52 and place them down in a particular order, well, n is 52, r is 5, so it's 52 factorial over 47 factorial. And if you have to calculate these things, don't calculate 52 factorial and divide by 47 factorial. Okay, they get big really fast. Do it by hand, because you can write the first few terms. Right, just write the first few terms, and you'll see that the tail of each of these cancels. Everything from 47 on down will cancel out. And so this complex expression is really just 52 times 51 times 50 times 49 times 48. And it's just a good old product rule popping up again. All right, if you have 10 people running a race and you're going to award 3 medals, how many different possible combinations are there? How many different ways, permutations, can the medals be assigned to the runners? So you want to pick 3 runners to get these medals, and the order matters, right? If this person gets gold and they get silver, that's different from the other one. So this is just the number of 3 permutations of 10 objects, which is just 10 factorial over 10 minus 3 factorial. So 10 factorial over 7 factorial. How many ways can you arrange the letters A, B, C, D, E, F, G such that the arrangement includes D next to E next to F. So we want to find the number of ways we can rearrange these 7 letters, but we're also requiring that that arrangement must have D followed by E followed by F immediately. And this is one that you can do a really hard way or a really easy way. Which one do you want to see?
Couldn't you just take the number of ways that you can arrange A, B, C, and G? Because D and F are always going to be the same.
They're going to be next to each other, but they could be anywhere in there. But yes, let's change this problem to say how many permutations are there of A, B, C, D, E, F, G, right? Those 5 objects. And so this is just the number of 5 permutations of 5 objects, which will be 5 factorial over 0 factorial. It's just 5 factorial, which is 120. That's the easy way. cool.
So for this problem, you just think of DEF as a single object.
Exactly, yeah. And hey, you can always change the problem to one that's easier to do. As long as it's got the same answer. That's another good math trick. So why is 0 factorial equal to 1? I mean, it makes this thing work nicely, but I mean, there's no 1 in sight, there's a 0. Maybe it's 0 just multiplied by itself, or maybe it's nothing multiplied. Factorials are like, n factorial is the product of the first n integers, right? So the product of the first 0 integers, what business do we have calling that 1?
But don't we do it because it fits the pattern?
Does it? It does.
We do it because we need it that way.
We need it that
To
way.
get the results that we know that they must be.
Yeah, this would not work if 0 factorial was 0, because we would end up with the number of permutations being something divided by 0, which gets us into all kinds of trouble with our math teachers. But that's not necessarily enough reason, right? If you turn in homework and you come up with a new procedure because you needed to do it in order to answer the question, right, that usually doesn't get you a lot of points. But there is a good reason why 0 factorial is equal to 1. And it's a quirky thing. It's a thing called Stirling's formula. No, it's... Nope, it's not Stirling's formula. It's a thing called the gamma function. So you've all done integral calculus to some degree, right? So so here's a really great definite integral. Integral from 0 to infinity of x to the z minus 1 times e to the minus x dx. And z can be an imaginary number, but we usually just talk about it as a real number. And it's a big, horrible integral to try to figure out. And it has this really funny graph that on the positive side, you know, starts off at infinity and swoops down and then goes back up pretty quickly. And it's undefined at 0, it blows up to infinity, and then from 0 to minus 1 it's negative, and it has this sort of upside down parabola shape, and it blows up at negative 1, and then it's a positive parabola shape, and then a negative, and it gets boxier as you go out, and it always blows up at these negative integer values. But on this positive side, the function value at 1 is 1, the function value at 2 is 1, the function value at 3 is 2, the function value at 4 is actually 6, and at 5 it's actually 24, and at 6 it's 120. And it turns out that gamma n is actually equal to n minus 1 factorial for positive integers n. So this is a function, you know, with an integral and an exponent and all this good stuff that turns out to be exactly equal to factorials for integer values of n. So if you calculate the integral of x to the 10th times e to the minus x dx from 0 to infinity, it'll turn out to be 10 factorial. And so we can use this to define what factorials are equal to for non-integers. And the argument is that, you know, since this function agrees with our notion of factorial for integers that are bigger than or equal to 1, we'll use this to extend the definition of factorials to other values. So this is something called Analytic Continuation, which is a really interesting alley to go down. And if you do that, if you evaluate this integral for z equals 1, right, this will give you 0 factorial, and the integral turns out to be equal to 1. And that's the reason why 1 factorial is the same as 0 factorial. But it's got some interesting peculiar values. For example, the gamma function at 1/2 somewhere in here. Gamma function at 1/2 is the square root of pi, which is kind of cool. So minus 1/2 factorial of square root of pi, or maybe 1/2 factorial.
And that's pretty strange.
Gamma 1/2 plus n is n factorial times the square root of pi times what we're going to call a combination, which is what we're talking about next. It's a number of unordered arrangements of n objects taken from n minus 1/2 objects. So there's all kinds of weird stuff, right? There's a double factorial. Those are big.
Wait, did you say 1/2 factorial equals the square root of pi?
These tend to go back and forth in my brain, so let me do gamma n equals
It kind of boggles the mind.
equals n minus 1 factorial.
I'm not sure I heard you correctly, but
Yeah, you probably did, but let me make sure.
pretty weird.
So gamma 1/2 would be negative 1/2 factorial, in some sense.
In some sense.
And there's the derivative of the gamma function, so that's kind of cool. And if you really want to lose some time over the weekend, Google into the Riemann Zeta-Function. And if it tickles your fancy, come and talk to me. I'll recommend a really good book on the subject. This has like consumed a number of people's lives. And it gets into the Riemann hypothesis, which is one of those, I think it's a millennial prize, right, $1 million. Gets into some really interesting aspects, but this is all interconnections between complex numbers and prime numbers and pi and e and all those good sorts of things. And it's all just kind of like hanging out there, you know, just waiting to be explored. All right, so 0 factorial is equal to 1. That's all you really need to know for this course. But there's other stuff there. Okay, so those are permutations. The extension of this is combinations. So a combination is an unordered arrangement of objects. And an R combination is an unordered arrangement of R objects. So for example, pick 3 people from a group of 5. And we don't care what order you place these people in. So if we try to use the product rule, right, our product rule would break this into 3 tasks. Pick the first person, pick the second person, pick the third person. The first person can be picked 5 different ways, the second one 4 ways, the third one 3 ways. So the total number of ways to do this is 5 times 4 times 3, right? That's just our permutation of 3 things taken from 5. but we don't care about the order. So if I pick person A followed by B followed by C, or I pick person B followed by A followed by C, those are considered the same selection of three people. If I use the product rule, if I look at permutations, this is counted as a different selection from that. So the number of commutations is generally going to be less than the number of permutations. And how much less, so this comes back to Randy's approach to doing permutations. Basically, this will tell us how many ways we can pick three people where we care about the order. For each group of three people, it's counting the number of ways we can arrange them as being separate selections. So if we take this and we divide it by the number of arrangements of three people, that will give us the number of combinations. So it's the number of permutations divided by the number of arrangements of those three people in this case. So we can cobble that into a nice formula.
Number of unordered arrangements of those three people?
It's the number of the number of unordered arrangements of R objects from N is the number of ordered arrangements divided by the number of ways we can order those R objects. Well, the number of ways you can order R objects is just the number of R permutations of R objects. So P of n comma R is n factorial over n minus R factorial. All right, that's this piece. And the number of R permutations of R objects is R factorial over R minus R factorial. Which is just R factorial over 0 factorial, which is just R factorial. So this is n factorial over n minus R factorial times R factorial. And we have a different symbol we usually use for writing combinations. So C of n comma R is written, and it's just parentheses with an R on top, an R on bottom and an n on top. It's not n divided by R, it's a totally new symbol. And we could say it's the number of R combinations of n objects. Or we could say it's n choose R. And there's different language. But we're basically taking permutations and then we're also dividing out by the number of arrangements of the objects we've chosen. So the number of ways to choose three people from a group of 5 is just 5 choose 3, which is 5 factorial over 2 factorial times 3 factorial, where this 2 was 5 minus 3. So the actual number of unique poker hands, because when you play poker you get 5 cards out of a deck of 52, and the order of those cards doesn't matter. If you have a 1, 2, 3, 7, 8, it's the same as having a 2, 3, 8, 7, 1. So the number of ways that you can pick 5 cards from 52, that's just 52 choose 5. It's 52 factorial over 47 factorial times 5 factorial. If you care about the order, you multiply this by the number of ways you can arrange 5 cards, which is 5 factorial, and you just end up with 52 factorial over 47 factorial, a number of permutations. So if we look at n-bit strings, strings comprised of n bits, ones or zeros, how many n-bit strings contain exactly r ones for some fixed value of r? Did you ever look at this when you were playing around with binary? So if we have 8-bit strings, how many contain 0 ones? Well, there's just one, that's a string of all zeros. How many 8-bit strings contain exactly a single one? That's going to be 8. It could be that, down to that. But how many 8-bit strings contain exactly 2 ones? Well, there's quite a few more, because those ones don't have to be next to each other. Sounds possible. So we can think of this in terms of combinations, right? Because what do you have? You have 8 positions, and we want to choose 2 of them to contain ones. And the order in which we choose them doesn't matter. If I choose this position and then that position, that corresponds to this number. If I choose this position first and then that position, that corresponds to the same number. So the order in which I choose these 2 positions does not matter. So I'm looking at combinations, the number of ways that I can choose 2 things out of 8. So that's 8 factorial over 6 factorial times 2 factorial. And so all of this stuff cancels, and so that's 56 over 2, so that's 28. Close. Number of ways that I can find bit strings containing 3 ones would be 8, 3. Number of things containing 4 ones, and so on. So here's an interesting factoid we'll come back to. Number of strings containing 0 ones, plus the number of strings containing 1 1, plus the number of strings containing 2 ones, etc., plus the number of strings containing 8 ones. What is that sum going to be equal to? Without doing the math. Forget the math. Think about it logically.
It's going to be all of them.
All of going to be all 8-bit strings, right? Because any 8-bit string either contains 0 ones, 1 1, 2 1, 7 ones, or 8 ones, right? So the number of strings with 0 ones plus the number of ones with 1 ones plus the number with 2 ones and so on equals total number of 8-bit strings, which is 2 to the 8th. And so we can make a general formula about combinations like that. And that's kind of cool, I think. Because we got combinations on the left which are factorial expressions, and we add them up and we just get power 2. That's kind of nice. And you can spend a lot of time just studying combinations. And we will do that on Friday for sure. But let me give you another interesting consequence of this. This is the number of ways that I can choose R objects from this set of n. So I got n objects, and I need to pick 3 of them. I'm going to say you, and you. Okay, I'm going to pick R objects. This is the number of ways I can do that. If I select R objects from n, have I also selected n minus R objects from n? If I have 8 bits and I've chosen 3 of them, I've automatically chosen 5 of them also. I've chosen 5 that I'm not going to pick. So by picking 3 objects out of n, I've also picked n minus 3 objects that I'm not going to select. And so this has got to be equal to this, just from a logical argument. Because selecting R objects is the same as choosing not to select n minus R objects. Right? The number of ways I can pick n minus R objects not to throw into my bag is exactly the same as the way I can pick R objects to put into my bag. And this holds water if you look at the formula. Because this is n factorial over n minus R factorial times R factorial. This is n factorial over n minus R factorial times n minus R factorial. And n minus R is just R. So it's exactly the same formulas. So there's a symmetry between these combinations. N choose R and n choose n minus R will give you the same value. All right, I'll leave you with something to ponder till Friday. This is not on the test. This is the let's make a deal question. So think about this if you want. And we can talk about answers on Friday. You're playing a game. You've got 3 doors, A, B, C. And there's a prize behind one of the doors. And the other 2 doors, there's no prize. Sometimes there's a tiger. But we'll just say there's no prize behind 2 of them. There's a prize behind one of them. And you have to choose which door you want to have opened. And if they open the door with the prize, you get the prize. Otherwise, you don't. Okay, so you make your selection. I don't know, I'm going to say B. Okay. And before they open a door, they will tell you another piece of information. They'll say, for example, it is not behind door A. Okay, or it's not behind door C. They're not going to tell you, they might tell you it's not behind B. So they give you a piece of information, a door that it's not behind. Okay, and they give you the option of changing your original guess. And the question is, are you better off changing your original guess, or does it not make a difference? And it's a fun question to think about, because it's one of those questions that the more you think about it, the more you convince yourself of a certain answer. And then if you keep thinking about it, you convince yourself that it's a different answer, and so on. But it's a fun one to think about, and it's not directly related to combinations, permutations, but it's the same kind of pathways in our brains. So pick an initial door, and they'll tell you either it's not behind A or it's not behind C. Should you change your guess, or should you stick with your original? Doesn't make any difference if you change. All right, so that's a freebie. So we will talk about more about combinations on Friday. We'll do a short quiz. We'll talk about Pascal's triangle.
Nice background.
Oh, thank you.